There is a photograph taken on February 14th, 1990. The Voyager 1 spacecraft, having completed its primary mission and now sailing through the outer reaches of the solar system, was instructed to turn its camera back toward the inner solar system for one final look. The resulting image shows a vast black field, the deep background of space, featureless and dark, and scattered across it a few streaks of light caused by sunlight scattering inside the camera optics. And in one of those streaks, barely distinguishable from the optical artifacts around it, is a pale blue dot. That dot is Earth. That dot is, as Carl Sagan famously described it, every human being who ever lived, every king and peasant, every mother and father, every inventor and explorer, every teacher and saint and sinner, every superstar and supreme leader, every young couple in love, every hopeful child, every parent who ever held a child, every act of courage and cowardice, every civilization in the history of our species, compressed into a point of light smaller than a single pixel in a photograph taken from 6 billion kilometers away. 6 billion kilometers. Voyager 1 was 6 billion kilometers from Earth when it took that photograph, and Earth was already a dot barely distinguishable from noise. And 6 billion kilometers is nothing. It is less than nothing. It is 0.000634 light years, 0.634 thousandths of a single light year. The nearest star to the Sun is 4.24 light years away. The Milky Way is 100,000 light years across. The nearest large galaxy is 2.5 million light years away. The observable universe is 93 billion light years in diameter. Voyager 1's distance from Earth at the time of the pale blue dot photograph, 6 billion kilometers, a distance that took the spacecraft 13 years of continuous travel at tens of thousands of kilometers per hour to cover, is not even a rounding error in the context of the observable universe. It is a subatomic particle in a football stadium. It is a bacterium in the Pacific Ocean. This video is about what the Earth actually is in the context of the universe. Not poetically, precisely, what the numbers mean, what they imply, what they feel like when you sit with them long enough to let them actually land. Because the scale of the universe relative to the Earth is not something that can be conveyed in a single comparison or a single photograph. It requires building the comparison step by step, layer by layer, moving outward from where we stand until the Earth is not just small, but is demonstrably, measurably, mathematically irrelevant as a physical object, a grain of calcium carbonate at the bottom of an ocean, while simultaneously being the only place in the known universe where the question of its own smallness has ever been asked. That tension between the physical insignificance of the Earth and the cognitive significance of the beings on it is what this video is actually about. There is a specific cognitive effect that happens when you genuinely engage with cosmic scale, not just intellectually, but viscerally. Astronomers have a name for something related, the overview effect, borrowed from the experience reported by astronauts who have seen the Earth from orbit. What astronauts describe is not merely an appreciation of the Earth's beauty, though that is part of it. It is a sudden, gut-level recalibration of significance, the realization, made physical and immediate by the view out the window, that the borders drawn on maps are invisible from space, that the planet is a single system that everything you have ever cared about, every relationship, every ambition, every fear, every grievance, is on that one small, fragile, luminous sphere. Edgar Mitchell, Apollo 14 astronaut, described looking at the Earth from the moon and feeling a sudden certainty that the universe is in some way conscious. Not a rational conclusion, but an overwhelming intuitive impression produced by the sheer incongruity of the Earth's beauty against the absolute darkness around it. Ron Garan, a space shuttle and ISS astronaut, described seeing the Earth as so impossibly delicate that it seemed a breath could extinguish it. This video is an attempt to induce a version of that effect from the ground. Not by putting you in a spacecraft, but by building the scale comparison step by step, layer by layer, with the actual numbers, until the Earth's smallness is not an abstract fact, but a genuinely felt reality. The numbers alone are not enough. Numbers like 93 billion light years or 200 billion stars are too large for the brain to process as anything other than vaguely large. The method here is to build the comparison iteratively, moving from the familiar to the barely imaginable, using analogies grounded in things you can actually picture, until the full scale of the comparison has accumulated enough weight to finally land. We are going to go through every level of the cosmic hierarchy, from the Earth to the observable universe, and at every level we are going to ask the same question: how big is the Earth compared to this? And at every level the answer will be the same, only more extreme. Let's start at home. Chapter 1. Starting here, the Earth in its own right. Before we can understand how small the Earth is, we need to understand how large the Earth is. Not large in the cosmic sense, that comes later, but large in the human sense. Large enough that for most of human history, its size was not known with any precision, and the attempt to measure it was considered one of the great intellectual achievements of antiquity. The Earth has a mean radius of 6,371 kilometers. Its circumference at the equator is approximately 40,075 kilometers. Its total surface area is about 510 million square kilometers, of which 71%, roughly 361 million square kilometers, is ocean. The remaining 29%, about 149 million square kilometers, is land. Its volume is approximately 1.08 times 10 to the 12th power cubic kilometers, a trillion cubic kilometers. Its mass is 5.972 times 10 to the 24th power kilograms. These numbers are large by human standards. 40,000 kilometers, the circumference, is roughly the distance you would travel if you circumnavigated the globe. If you drove at highway speed without stopping 24 hours a day, it would take you approximately 17 days to cover that distance. If you walked at a brisk pace 8 hours a day, it would take about 500 days, a year and a half of continuous walking. The Earth is large enough that the great explorers who first circumnavigated it did so over years in ships and counted it among the supreme physical achievements of the age. The first reasonably accurate measurement of the Earth's circumference was made by Eratosthenes of Cyrene around 240 BCE, using a method of extraordinary elegance. Eratosthenes knew that at noon on the summer solstice, the sun shone directly down a well in Siena, modern-day Aswan, Egypt, casting no shadow. The the sun was directly overhead. On the same day in Alexandria, a vertical stick cast a shadow at an angle of about 7.2 degrees from vertical. Eratosthenes reasoned that since the sun's rays are effectively parallel at the Earth's surface, the sun being so far away, the 7.2 degree angle represented the difference in latitude between Alexandria and Siena. Since 7.2 degrees is 1/50th of 360 degrees, the distance between the two cities must be 1/50th of the Earth's total circumference. He knew the distance between the cities was approximately 5,000 stadia from travelers' accounts, so he calculated the circumference as 250,000 stadia. Depending on which value of the stadion you use, the unit varied regionally. This gives a circumference of 39,375 to 46,620 kilometers. The actual value is 40,075 kilometers. Eratosthenes was accurate to within a few percent, using nothing but geometry, curiosity, and the angle of a shadow. This tells you something important about the Earth's size. It is large enough to be a geometric puzzle requiring ingenuity to solve, but small enough that a shadow angle and a travel distance were sufficient to determine its circumference. The Earth is a planet. It is a body large enough to be spherical under its own gravity. The threshold for hydrostatic equilibrium, at which point an object's self-gravity is stronger than the material strength of its rock, causing it to assume a roughly spherical shape, falls at a diameter of a few hundred kilometers for rocky bodies. The Earth, at 12,742 kilometers in diameter, is well above this threshold. It is a proper planet, geologically active, with a molten iron core generating a magnetic field, a layered structure of crust, mantle, and core, plate tectonics reshaping its surface over geological time, an atmosphere that has been chemically modified by 4 billion years of biology, and at least one large moon formed by a massive impact early in its history. It is, in other words, an impressively complex and dynamic object. The Earth is old, 4.54 billion years old, formed from the accretion of the solar nebula and shaped by the collision of the proto-Earth with a Mars-sized body called Theia, which produced the moon and reset the geological clock. In 4.54 billion years, the Earth has been reshaped by plate tectonics, bombarded by asteroids in a period called the Late Heavy Bombardment, frozen into global glaciations at least twice, the Snowball Earth episodes, and warmed by the gradual brightening of the sun. It has hosted life for approximately 3.8 billion years. From the first single-celled organisms in the early oceans to the 8.7 million species estimated to exist today, of which humanity has formally described about 1.2 million. The Earth is not just a rock. It is a living system, in the deepest sense of that phrase. A planet whose surface, atmosphere, hydrosphere, and biosphere are coupled in feedback loops that regulate temperature, chemistry, and the conditions for life. And all of that complexity, all 4.54 billion years of geological and biological history, all 8.7 million species, all the oceans and mountains and ice sheets and atmospheric chemistry, occupies a sphere 12,742 kilometers in diameter. A sphere that, in the context of the observable universe, is smaller than the smallest thing you can imagine. It is the standard unit of measurement for everything that comes next. Every comparison that follows is going to be made in terms of Earths, multiples of the Earth's size, mass, or volume, because that is the only way to give the numbers a human hook to grab onto. Let's go. Chapter 2: The Moon, the first step outward. The Moon is 384,400 kilometers from Earth, on average. This is the distance between the centers of the two bodies. The Moon's surface is about 378,000 kilometers from Earth's surface, a distance that changes throughout the month as the Moon's elliptical orbit brings it closer at perigee, about 362,600 kilometers from Earth's center, and farther away at apogee, about 405,400 kilometers. The Apollo missions took about 3 days to cover this distance. The Moon has a diameter of 3,474 kilometers, about 27% of Earth's diameter. Its volume is about 2% of Earth's volume. Its mass is about 1.2% of Earth's mass. If Earth were a basketball, the Moon would be a tennis ball, and the distance between them, to scale, would be about 7.3 meters. Roughly the distance across a large living room. That is the first step in our scale model. A basketball, a tennis ball, 7 meters apart. This distance is the one that humanity has actually physically crossed. 12 human beings have stood on the surface of the Moon. All 12 are now dead. The last human to walk on the Moon was Eugene Cernan in December 1972, over 50 years ago. The 384,400 kilometers between Earth and Moon is the only distance beyond the Earth's atmosphere that human beings have ever directly traversed. Every other distance we will discuss in this video, from the Sun to the edge of the solar system, to the nearest star, to the galaxy, to the observable universe, has been crossed only by light and by the unmanned probes we have sent outward. The Apollo program remains one of the most remarkable logistical and engineering achievements in human history. The Saturn V rocket that launched Apollo 11 to the Moon in July 1969 stands 110 meters tall, taller than the Statue of Liberty, and generated 34 million newtons of thrust at liftoff, burning through 12,000 kilograms of propellant per second in its first stage alone. It is the most powerful rocket ever successfully flown, and the payload it delivered to the Moon, the command module, service module, and lunar module, weighed less than 50,000 kilograms at lunar orbit. To cross 384,400 kilometers, humanity built a 2.8 million kilogram machine that burned almost entirely before it arrived. The mass ratio of the Saturn V, the ratio of launch mass to payload mass at the destination, was about 56-1. Getting to the Moon and getting back required a machine almost entirely made of fuel. This gives you an immediate physical intuition for why interstellar travel is not merely an engineering challenge, but a challenge of a qualitatively different order of magnitude. The Moon distance is important as a baseline because it is simultaneously the largest distance any human being has ever directly traveled, and a distance so small relative to the rest of the universe that it does not register. The Moon is, in cosmic terms, essentially adjacent to the Earth. A thin sliver of space, a local neighborhood detail, entirely negligible at any scale larger than the solar system. the Earth-Moon distance of 384,400 kilometers is 1.28 light seconds, the time it takes light to cross the gap. Our scale begins. Chapter 3: The Sun. Where the scale first becomes uncomfortable. The Sun is 149.6 million kilometers from Earth on average. This distance, defined as 1 astronomical unit, or 1 AU, is the fundamental unit of distance within the solar system. Light covers this distance in approximately 8 minutes and 20 seconds. When you look at the Sun, briefly and with proper protection, you are seeing it as it was 8 minutes ago. The Sun is not merely larger than the Earth, it is incomparably larger. The Sun's diameter is 1,392,700 kilometers, approximately 109 times the diameter of Earth. Its volume is approximately 1.3 million times the volume of Earth, meaning you could fit 1.3 million Earths inside the Sun. Its mass is 1.989 times 10 to the 30th power kilograms, approximately 333,000 times the mass of Earth. The Sun contains 99.86% of all the mass in the solar system. Everything else, all 8 planets, all their moons, all the asteroids, comets, Kuiper belt objects, and dust, constitutes the remaining 0.14%. If the Earth were a grape, roughly 1.5 centimeters in diameter, the Sun would be a sphere about 1.6 meters in diameter. The size of a large exercise ball or a small hot tub. And the distance between the grape and the exercise ball, to scale, would be approximately 170 meters. Imagine a grape on one end of 2 football fields, with an exercise ball on the other end. That is the Earth-Sun system at human scale. The Sun is a star. Specifically, it is a G-type main sequence star, a yellow dwarf, though its actual color when seen from space is closer to white. It is classified as a dwarf by stellar standards, not because it is particularly small among stars, but because it has not yet evolved off the main sequence into a subgiant or giant. Among all the stars in the Milky Way, the Sun is actually fairly average in mass, but larger than about 90% of all stars by radius, because the most common stars in the galaxy are small red dwarfs significantly smaller than the Sun. The Sun is converting approximately 600 million tons of hydrogen into helium every second through the process of nuclear fusion in its core, releasing energy at a total rate of 3.83 times 10 to the 26th power watts. It has been doing this for 4.6 billion years, and it has enough hydrogen fuel remaining to continue for approximately another 5 billion years. The Sun is so much larger than the Earth that the comparison strains comprehension even before we leave the solar system. But the Sun is not the largest star, not close to the largest star. There are stars in the Milky Way that dwarf the Sun to the same degree that the Sun dwarfs the Earth. UY Scuti, a red supergiant in the constellation Scutum, has a radius approximately 1,700 times the radius of the Sun. If placed at the center of the solar system, its photosphere would extend past the orbit of Jupiter. Stephenson 2-18, another red supergiant, may be even larger, with a radius up to 2,150 times that of the Sun, extending past the orbit of Saturn if placed at our solar system's center. These stars are so large that the Earth, relative to them, is approximately what a bacterium is relative to the Earth. Not a metaphor, an order of magnitude estimate that is accurate to within a factor of a few. But we have not yet left the solar system. We are still at 1 astronomical unit, 8 light minutes from home. Chapter 4. The solar system, 8 planets, 1 star, and an enormous amount of nothing. The solar system extends far beyond the orbit of the 8 planets. The classical boundary, the orbit of Neptune, at about 30 astronomical units, is merely where the major planets end. The solar system, properly speaking, extends to the heliopause at about 100 astronomical units, where the solar wind meets the interstellar medium, which is where Voyager 1 currently is, to the scattered disk and Kuiper belt at 30 to 1,000 astronomical units, and to the Oort cloud, a vast spherical shell of comets and icy bodies, at somewhere between 2,000 and 200,000 astronomical units, if you include the Oort cloud. As part of the solar system, the Sun's gravitational sphere of influence extends roughly halfway to the nearest star. Let's put some of these distances in context. Neptune, the outermost planet, is on average 30 astronomical units from the Sun, about 4.5 billion kilometers. Light takes about 4 hours to travel from the Sun to Neptune. The New Horizons spacecraft, which launched in January 2006 and flew past Pluto in July 2015, is currently traveling through the Kuiper belt at about 50 astronomical units from the Sun, and it launched nearly 20 years ago. Voyager 1 launched in 1977, and now the farthest human-made object from Earth at approximately 165 astronomical units has been traveling for nearly 50 years and is just barely past the heliopause, the boundary of the Sun's direct influence. And it is not even a quarter of the way to the inner edge of the Oort cloud. The solar system is large. It is also almost entirely empty. The total volume enclosed by Neptune's orbit, the sphere of radius 30 astronomical units, is approximately 1.14 times 10 to the power of 36 cubic meters. The total volume of all 8 planets combined is approximately 4.4 times 10 to the power of 24 cubic meters. This means that the planets, combined, occupy about 3.8 times 10 to the power of minus 12 of the total volume enclosed by Neptune's orbit, less than 4 trillionths of the available space. If you shrank the entire solar system to the size of the Earth, the combined volume of all 8 planets would be about the size of a virus. The solar system is not a collection of planets with some space between them. It is an enormous sphere of essentially empty space, with a star at the center and some small, widely separated objects distributed sparsely throughout. It is worth pausing on Voyager 1 specifically, because its journey is one of the most concrete illustrations of solar system scale available to us. Voyager 1 launched on September 5, 1977, nearly 50 years ago. It has been traveling continuously in an essentially straight line outward from the Sun at speeds between 56,000 and 61,000 kilometers per hour, depending on gravitational effects from planetary flybys and the solar wind. In those 5 decades of continuous travel, it has covered approximately 24 billion kilometers, about 165 astronomical units, It crossed the orbit of Pluto in 1990. It crossed the termination shock, the boundary where the solar wind begins to slow as it meets the interstellar medium, in 2004. It officially crossed the heliopause, the outer boundary of the Sun's direct influence, in August 2012, making it the first human-made object to enter interstellar space. And yet, by galactic standards, Voyager 1 has gone nowhere. After 50 years of travel at 61,000 kilometers per hour, it is 165 astronomical units from the Sun. Alpha Centauri, the nearest star, is approximately 268,000 astronomical units away. Voyager 1, on its current trajectory and at its current speed, would take approximately 73,000 years to reach Alpha Centauri if it were headed there, which it is not. The distances between stars are not merely large. They are large in a way that existing human technology cannot address. Voyager 1 is not even 0.1% of the way to the nearest star. Now, let's look at the Earth specifically within this context. At 1 astronomical unit from the Sun, in a solar system that extends to at least 100 astronomical units at the heliopause, the Earth's orbital radius is 1% of the distance from the Sun to the heliopause. The Earth occupies a position in the solar system equivalent to a dust grain 1 centimeter from the center of a sphere 1 meter in radius. If you made a scale model of the solar system, accurate to scale, so that the sizes of the bodies and the distances between them are both to scale, you would need a model several kilometers across to make any of the planets visible to the naked eye. And even then, the planets would be microscopic dots. The famous model that makes this viscerally clear is the one proposed by Chet Ramo and executed in various forms. Place a grapefruit, representing the Sun, at one end of a chu space and walk outward. Mercury would be a grain of sand about 5 meters away. Venus, another grain of sand, at 9 meters. Earth, yet another grain of sand at 13 meters. Mars, a smaller grain of sand, at 20 meters. Jupiter, a marble, at 68 meters. Saturn, a slightly smaller marble, at 125 meters. Uranus, a pea, at 250 meters. Neptune, another pea, at 390 meters. You would need a space 390 meters long, nearly a quarter of a mile, to accommodate the 8 planets. And the Sun at one end would be the size of a grapefruit. Earth, at 13 meters from the Sun, would be a grain of sand 1.2 millimeters in diameter. That is the Earth in the solar system, and the solar system is nothing. It is the tiniest subunit of a galaxy that itself is tiny compared to what comes next. Chapter 5: The Nearest Star, the first truly interstellar distance. Beyond the solar system, the next landmark is the nearest star system, Alpha Centauri, a gravitationally bound system of 3 stars, Alpha, Centauri A, Alpha Centauri B, and Proxima Centauri, located approximately 4.24 light-years from the Sun, the distance to Proxima, the nearest of the 3, 4.24 light-years. This is the distance that light, traveling at 299,792,458 meters per second, the fastest anything in the universe can move, covers in 4.24 years. It is approximately 40 trillion kilometers, 40,000 billion kilometers. In the scale model, where the Sun is a grapefruit at one end of a 390-meter space, The nearest star, Alpha Centauri, would be another grapefruit located approximately 3,500 kilometers away. Not 3,500 meters. 3,500 kilometers? The distance from New York to Los Angeles, roughly. If your solar system model started in New York, the nearest star would be in Los Angeles. And between those two grapefruits, between the Sun and Alpha Centauri, there would be nothing except the occasional hydrogen atom and some CMB photons. No planets, no gas clouds of any significance, no objects of any kind, just empty interstellar space for 40 trillion kilometers. The fastest spacecraft ever launched by humanity is the Parker Solar Probe, which at its closest approach to the Sun reaches speeds of approximately 692,000 kilometers per hour. At this speed, which is only achievable near the Sun due to gravitational acceleration, it would take approximately 6,600 years to reach Alpha Centauri. Voyager 1, currently traveling at about 61,000 kilometers per hour relative to the Sun, would take approximately 73,000 years to cover the same distance, though it is not headed in that direction. The fastest proposed propulsion concepts that are currently within the realm of theoretical engineering, laser-driven light sails of the kind studied by the Breakthrough Starshot Initiative, could potentially achieve speeds of 20% of the speed of light and would still take about 20 years to reach Alpha Centauri. 20 years on the fastest spacecraft that current physics and engineering can conceive of to cover the distance to the nearest star. And the nearest star is, by galactic standards, right next door. In the context of this distance, the Earth is not small. It doesn't have a size at all in any meaningful sense. At the scale of interstellar distances, the Earth is a mathematical point, a location marker, not a physical object with detectable extent. The Earth's diameter of 12,742 kilometers, measured against the 40 trillion kilometer distance to Alpha Centauri, is a ratio of roughly 1 to 3 billion. If Alpha Centauri were represented by a point 1 meter away from the Sun in a scale model, the Earth's diameter would be less than half a nanometer, smaller than a single atom. The Earth has ceased to be a physical object at this scale. It has become a coordinate. But there is something more to say about what interstellar distances mean in practical terms, because the numbers alone do not capture the qualitative shift they represent. Within the Chart solar system, communication is possible in minutes to hours. We talk to the Voyager probes in real time, or nearly real time. Mission controllers can send a command to a spacecraft orbiting Mars and receive a confirmation in 20 to 40 minutes. This is inconvenient but manageable. Interstellar communication is fundamentally different. A radio message sent to Alpha Centauri today would arrive in 4.24 years. A reply would arrive back 4.24 years after that. A single exchange of messages, a question and an answer, takes 8.5 years. A conversation is physically impossible. A civilization at Alpha Centauri could know about our existence from our radio leakage only if the signals have had time to reach them, which in this case, they have. We have been broadcasting radio since the early 20th century. But any response they might have sent us would not arrive for years after they detected us, and we would have to wait years more for any reply to our reply. The interstellar void does not just impose distance. It imposes a minimum response time that is measured in years, a communication lag that makes interstellar dialogue structurally different from any form of communication human beings have ever practiced. This is why the Earth's smallness at interstellar scales is not just a matter of physical size. It is a matter of isolation. The Earth is physically separated from even its nearest stellar neighbor by a gap so large that the fastest thing in the universe, light, takes years to cross it. We are, in the most literal sense, alone in our corner of the galaxy, not because there is nothing else in the galaxy, but because the distances are too large for meaningful interaction on human timescales. Chapter 6. The Milky Way, 100,000 light-years of irrelevance. The Milky Way is the galaxy that contains our solar system. It is a barred spiral galaxy, meaning it has a central bar of stars running through its nucleus, from which two main spiral arms emerge, with a disk diameter of approximately 100,000 to 120,000 light-years, and a thickness of roughly 1,000 light-years at our location. Though the disk varies in thickness and has a warped shape at its edges, it contains somewhere between 200 and 400 billion stars. Its total mass, including the dark matter halo that surrounds the visible disk, is approximately 1 to 1.5 trillion solar masses, of which only a small fraction is in the visible stars, gas, and dust. The dark matter halo extends much farther than the visible disk, to perhaps 200,000 to 300,000 light-years from the galactic center. Our solar system is located approximately 26,000 light-years from the galactic center in the Orion Arm, a minor spiral arm between two larger spiral arms called the Sagittarius Arm and the Perseus Arm. We are not in the center of the galaxy, not in one of the main spiral arms, and not in the outer reaches of the disk. We are in a moderately populated intermediate region at about 56% of the way from the galactic center to the edge of the disk. The solar system orbits the galactic center at a speed of approximately 220 kilometers per second. At this speed, a complete orbit of the galaxy, a galactic year, takes approximately 225 to 250 million years. The solar system has completed about 20 galactic orbits since it formed. The last time the solar system was in its current galactic position, the dominant land animals on Earth were early dinosaurs. Now, how does the Earth fit into this picture? The Milky Way disk is 100,000 light-years in diameter. The Earth's orbit around the Sun has a diameter of 2 astronomical units, 300 million kilometers. Converting to light-years, 2 astronomical units is about 3.17 times 10 to the power of -5 light-years. The ratio of the Milky Way's diameter to the diameter of the Earth's orbit is therefore approximately 3.15 billion. And the Earth itself, with a diameter of 12,742 kilometers, is about 77,000 times smaller than its orbital diameter. So the ratio of the Milky Way's diameter to the Earth's physical diameter is approximately 77,000 times 3.15 billion, which comes to roughly 2.4 times 10 to the 14th power, 240 trillion. The Milky Way is 240 trillion times wider than the Earth. If the Milky Way were scaled to the size of the continental United States, about 4,500 kilometers across, the Earth would be a sphere about 19 micrometers in diameter. A human hair is approximately 70 micrometers in diameter. The Earth would be about 1/4 the width of a human hair, somewhere in the middle of the continental United States, in that scale model. You could not see it. You could not feel it. It would require a powerful microscope to detect. The Earth, against the scale of the Milky Way, is not a grain of sand. It is smaller than a bacterium. The Milky Way contains between 200 and 400 billion stars. Each of those stars is a sun. Most of them are smaller and dimmer than ours. About 70 to 75% of all stars in the Milky Way are M-type red dwarfs, with masses ranging from 8 to 60% of the Sun's mass. But many are similar to the Sun, and some are much larger. Recent surveys suggest that the fraction of Sun-like stars with Earth-sized planets in roughly habitable orbits is somewhere between 10 and 50%. If we take the conservative end, 10%, and apply it to 200 billion stars, we get 20 billion potentially Earth-like planets in the Milky Way alone. If we take the other end, we get 100 billion. The universe, even within a single galaxy, may be teeming with Earth-like planets. Earth is not unique in character, perhaps, only in the fact that it is ours, and that we are here. The Milky Way is vast. It is so vast that even the fastest radio signal we have ever sent, the Arecibo message of 1974, traveling at the speed of light, has covered only about 50 light years of the galaxy's 100,000 light years in the time since it was transmitted. It will take 2,000 years to reach the galactic center. It will take 100,000 years to cross the galaxy. By the time it reaches the other side, human civilization, if it still exists in any recognizable form, will have had time to evolve and change as much as it has changed since before the invention of writing. The Milky Way is not just large. It is large in a way that makes human timescales irrelevant. It is also worth dwelling on what the Milky Way looks like from outside. Or rather, what we infer it looks like, since we have never been outside it and almost certainly never will be. We know the Milky Way is a barred spiral galaxy from indirect evidence, from radio observations of neutral hydrogen tracing the spiral arms, from infrared surveys revealing the central bar, from comparisons with external galaxies of similar mass and rotation speed. The image of a spiral galaxy you have in your mind when you picture the Milky Way is reconstructed from observations made from inside it, like trying to draw a map of the building you are in by looking through the walls. Our best current model suggests a galaxy with two main spiral arms, the Scutum Centaurus arm and the Perseus arm, and several smaller arm segments, including the Orion arm where we are located. The galactic center, Sagittarius A star, the supermassive black hole at the heart of the Milky Way, is approximately 26,000 light years from the Sun. It has a mass of approximately 4 million solar masses. At 26,000 light years distance, it poses no direct threat to the solar system. The tidal effects of even a 4 million solar mass black hole fall off rapidly with distance, but it is the gravitational anchor around which everything in the galaxy orbits. The Sun has been orbiting Sagittarius A star for approximately 4.6 billion years. In that time, Sagittarius A star has likely consumed enormous amounts of gas and stars, briefly blazing as a quasar billions of years ago when gas accretion was at its peak, and has since settled into a relatively quiescent state. The center of the Milky Way is not empty. It is crowded with stars, stellar remnants, gas clouds, and the various exotic phenomena associated with a supermassive black hole at close range. But from our vantage point 26,000 light-years out, it is simply a bright region in the direction of Sagittarius, partially obscured by the dust of the galactic plane. Chapter 7. The Local Group, Our Gravitational Family. The Milky Way is not alone. It is part of a gravitationally bound collection of galaxies called the Local Group, a cluster of roughly 80 galaxies that share a common gravitational destiny. The Local Group spans approximately 10 million light-years in diameter and has a total mass of approximately 2 times 10 to the 12th solar masses, about 2 trillion solar masses. The two largest members of the Local Group are the Milky Way and the Andromeda Galaxy, also known as M31 or NGC 224. Andromeda is a spiral galaxy of similar type to the Milky Way, but significantly larger. Its disk is estimated to be about 220,000 light-years in diameter, though estimates vary as the edges of galaxies are not sharply defined. And it contains roughly 1 trillion stars compared to the Milky Way's 200 to 400 billion. Andromeda is currently approximately 2.537 million light-years away from the Milky Way. The light you see when you look at Andromeda with the naked eye on a clear night left that galaxy 2.537 million years ago, before modern Homo sapiens existed. The galaxy you are seeing is a fossil image from the Pleistocene. Andromeda is approaching the Milky Way. The two galaxies are on a collision course, moving toward each other at approximately 110 kilometers per second. In approximately 4.5 billion years, the Andromeda Galaxy and the Milky Way will collide and emerge, producing a large elliptical galaxy that some astronomers have nicknamed Milkomeda. This collision will not be catastrophic for individual stars. Galaxies are so empty that stellar collisions during a galaxy merger are extremely rare, but it will reshape the structure of both galaxies entirely, disrupting the spiral arms, flinging stars into new orbits, and eventually producing a single, more diffuse elliptical galaxy, rotating slowly around a merged supermassive black hole. Our Sun will survive this collision. The Earth will survive. The night sky will change dramatically over millions of years as the two galaxies interact, but the individual stars and their planetary systems will largely endure. What will not survive intact is any sense of the Milky Way as a distinct entity. Beyond the Milky Way and Andromeda, the other members of the Local Group are mostly small, dwarf galaxies ranging from a few million to a few tens of billions of stars. The Magellanic Clouds, the Large and Small Magellanic Cloud, are the most prominent, being irregular dwarf galaxies visible with the naked eye from the southern hemisphere at distances of 160,000 and 200,000 light-years, respectively. They are gravitationally interacting with the Milky Way and are likely in the process of being absorbed by it over billions of years. The Earth's position within the Local Group is roughly central. The Milky Way sits near the center of mass of the Local Group along with Andromeda, which it is gravitationally paired with. The smaller galaxies orbit around the two main members. The Earth is therefore not in the most remote part of the local group, but it is on no particularly special position either. It is simply where the third planet of an ordinary star happens to be, in one of the two dominant galaxies of a small galaxy cluster. The local group itself is a minor feature of the next level up. Chapter 8: The Virgo Supercluster and Laniakea. The address gets longer. Galaxy clusters, gravitationally bound collections of a few dozen to a few thousand galaxies, are themselves grouped into superclusters, which are the largest gravitationally coherent structures in the universe. The local group is part of the Virgo supercluster, also called the local supercluster, which is centered on the Virgo cluster, a massive galaxy cluster containing over 1,300 galaxies, about 65 million light-years away. The Virgo supercluster as a whole is approximately 110 million light-years in diameter and contains an estimated 47,000 galaxies. The Milky Way, and therefore the Earth, is in the outskirts of this supercluster, near its edge, in a relatively sparse region dominated by the local group. In 2014, a team of astronomers led by R. Brent Tully, Hélène Courtois, Yehuda Hoffman, and Daniel Pomerade published a redefinition of our supercluster boundaries based on a new method, mapping the flow of galaxies in the local universe. Galaxies do not merely recede from each other with the Hubble flow. They also have peculiar velocities caused by the gravitational pull of overdense regions. By mapping these peculiar velocity flows, Tully's team identified a vast supercluster structure, all galaxies whose gravitational infall converges toward a common center, that they named Laniakea from the Hawaiian words for immeasurable heaven. Laniakea is approximately 520 million light-years in diameter and contains the mass of approximately 100 million billion solar masses, 10 to the power of 17 solar masses. It encompasses approximately 100,000 galaxies, including the Milky Way and all of the Virgo supercluster. It is bounded not by walls of higher density, but by boundaries where the gravitational flow diverges, where galaxies on one side are being pulled toward one attractor, and galaxies on the other side toward a different attractor. The Milky Way sits in the outer edge of Laniakea in a tendril of the supercluster structure, far from the gravitational center. The center of Laniakea's gravitational attraction, the Great Attractor, is in the direction of the constellation Centaurus, at a distance of about 150 to 250 million light-years, in the Norma cluster region. Everything within Laniakea, including the Milky Way, is falling toward this great attractor at several hundred kilometers per second. The Earth is not stationary relative to the large-scale structure of the universe. It is in orbital motion around the Sun, 30 kilometers per second. The Sun orbits the galactic center, 220 kilometers per second. The Milky Way moves toward Andromeda, 110 kilometers per second. And the local group falls toward the Virgo cluster and ultimately the Great Attractor at roughly 600 kilometers per second relative to the CMB rest frame. At the scale of Laniakea, 520 million light-years, the Earth is not just a coordinate, it is smaller than a coordinate. There is no unit of distance commonly used in cosmology that is smaller than a kiloparsec, about 3,260 light-years, and the Earth's size in kiloparsecs is approximately 4 times 10 to the minus 16 kiloparsecs. A number so small it has no practical meaning at this scale. Laniakea is 160,000 kiloparsecs in diameter. The Earth's physical size contributes nothing to that number in any digit that a calculator would display. The Earth is, at the scale of the supercluster, not absent. It is below the threshold of representation, not a rounding error, below the precision of the instruments we use to describe things at this scale. What is striking about Laniakea is not just its size, but the motion it implies. The entire supercluster, all 100,000 galaxies, all the matter within 260 million light years in every direction of our position, is moving together, falling towards the great attractor at hundreds of kilometers per second. This is not a trivial motion. The great attractor is a region of space with an anomalously high mass concentration, pulling everything around it gravitationally. For a long time, astronomers could not directly observe it because it lies almost directly behind the plane of the Milky Way, the zone of avoidance, where the dust and gas of the galactic disk block optical observations. It was detected first through its gravitational effects on the peculiar velocities of galaxies. Subsequent observations in X-ray and radio wavelengths, which are less affected by galactic dust, revealed the Norma cluster at its approximate location, along with the broader Shapley supercluster behind it at a distance of about 650 million light-years, a massive concentration that may also be contributing significantly to the local gravitational flow. The Earth is not sitting still in the universe. Nothing in the universe sits still. The Earth moves at 30 kilometers per second around the Sun. The Sun moves at 220 kilometers per second around the galactic center. The Milky Way moves toward Andromeda at roughly 110 kilometers per second. The local group falls toward the Virgo cluster. The whole assemblage falls toward the great attractor at roughly 600 kilometers per second relative to the CMB frame. The Earth is a passenger on a vast gravitational cascade, a chain of motions, each nested within the next, each caused by the gravity of the structures at the next level up. The Earth does not orbit the Sun in isolation. It participates, whether it knows it or not, in the dynamics of the supercluster. Chapter 9. The Observable Universe, the Final Scale. We have traveled from the Earth to the Moon, from the Moon to the Sun, from the Sun to the edge of the solar system, from the solar system to the nearest star, from the nearest star across the Milky Way, from the Milky Way through the local group, and from the local group through Laniakea. At each step, the Earth has become smaller. First a grain of sand in a grapefruit model, then a point smaller than an atom, then below the threshold of representation entirely. And we have not yet reached the final scale. Beyond Laniakea, the cosmic web extends. The filaments and voids of the large-scale structure, which we discussed in previous videos, stretch across hundreds of millions and billions of light-years. Laniakea itself is a single node in this structure. Supercluster, feeding into the broader network of filaments that connects the largest concentrations of matter in the observable universe. Beyond Laniakea are other superclusters: the Perseus-Pisces supercluster, the Coma supercluster, the Shapley supercluster, the largest known concentration of galaxies in the local universe, at a distance of about 650 million light-years. and a mass of roughly 10 million billion solar masses. These are features of the cosmic web's architecture, visible in the large-scale galaxy maps assembled by the Sloan Digital Sky Survey and its successors. And beyond all of them, beyond every supercluster and filament and void that has been mapped, beyond every galaxy whose light has reached a telescope, is the edge of the observable universe. Not the edge of the universe itself, which has no known edge, but the edge of what light has had time to reach us from since the Big Bang. The cosmic horizon at a co-moving distance of approximately 46.5 billion light-years in every direction, giving the observable universe a diameter of approximately 93 billion light-years. Let's put this number against the Earth one final time. The Earth's diameter is 12,742 kilometers. Convert to light-years. 12,742 kilometers is approximately 1.346 times 10 to the minus 12 light-years, roughly 1/trillionth of a light-year. The observable universe's diameter is 93 times 10 to the 9th power light-years, 93 billion light-years. The ratio of the observable universe's diameter to the Earth's diameter is therefore 93 times 10 to the 9th power, divided by 1.346 times. 10 to the power of minus 12 equals approximately 6.9 times 10 to the power of 22. That is 69 sextillion. The observable universe is approximately 69 sextillion times wider than the Earth. Written out, 69 sextillion times wider. If you shrunk the observable universe to the diameter of the Earth, 12,742 kilometers, the actual Earth would be approximately 1.8 times 10 to the power of minus 13 meters across. That is 0.0000000000018 meters. For reference, a hydrogen atom has a diameter of about 1.06 times 10 to the power of minus 10 meters. The scaled down Earth would be approximately 580 times smaller than a hydrogen atom, smaller than a proton. The Earth, against the scale of the observable universe, is subnuclear. It is smaller than the nucleus of the smallest atom. There is no analogy that adequately captures this ratio. Every analogy breaks down because no object in ordinary experience spans 22 orders of magnitude. But let us try anyway. Not because the analogy will succeed, but because the failure of the analogy is itself informative. Imagine a single grain of fine sand, about half a millimeter in diameter, 0.0005 meters. Now imagine the Milky Way galaxy, 100,000 light-years across. The ratio of the Milky Way to a grain of sand is roughly 10 to the 24th power, somewhat larger than the ratio of the observable universe to the Earth, but in the same ballpark. So the Earth against the observable universe is roughly like a grain of sand against the Milky Way. You already cannot picture the Milky Way. You already cannot imagine what it means to be a grain of sand compared to something you cannot picture. The analogy does not produce intuition. It produces a faint, vertiginous sense of the failure of intuition, and that is the closest we can get. There is one more number that puts the observable universe's scale in context in a specific and useful way. The observable universe contains approximately 2 times 10 to the 12th power galaxies, 2 trillion galaxies. Each of these galaxies contains, on average, perhaps 10 to the power of 11 stars, 100 billion stars. The total number of stars in the observable universe is therefore approximately 2 times 10 to the 23rd power, 200 sextillion stars. For comparison, the total number of grains of sand on all of Earth's beaches and deserts is estimated to be approximately 7.5 times 10 to the 18th power, 7.5 quintillion grains. The number of stars in the observable universe is about 26,000 times larger than the number of grains of sand on Earth. Every single grain of sand on the entire surface of the Earth represents 26,000 stars, and around each of those stars, there may be planets, and around some of those planets, there may be moons. The observable universe is not just larger than the Earth. It is larger than the Earth by a margin that makes the Earth literally incomparable to it by any standard method of comparison. The comparison breaks mathematics. You have to just sit with the number and let it be what it is. There is something else worth noting about the 93 billion light-year figure that trips people up. It is larger than the age of the universe in light years. The universe is 13.8 billion years old. Light travels 1 light year per year. So shouldn't the farthest light that could have reached us come from a distance of at most 13.8 billion light years? The resolution to this apparent paradox is that the universe has been expanding throughout its history. The galaxies whose light we are currently receiving were much closer to us when they emitted that light than they are now. In the time the light has been traveling, those galaxies have been carried farther away by the expansion of space. The galaxy whose light has just reached us after 13.8 billion years of travel is now about 46.5 billion light years away? Not 13.8 billion, because the space between us and it expanded while the light was in transit. The observable universe is larger than 13.8 billion light years, for the same reason that a ball thrown across a room travels farther than its original throw distance if the room is stretching. The expansion of space is not a motion of galaxies through space. It is the stretching of space itself, and there is no speed limit on how fast space can stretch. Distance can grow faster than light. Light emitted by distant galaxies does not catch up with us immediately. It travels through an expanding medium, and whether it ever reaches us depends on whether the expansion is fast enough to outrun it. Galaxies beyond the cosmological event horizon, currently about 16 billion light years away, are receding faster than light can cross the gap, and their light will never reach us no matter how long we wait. The observable universe at 46.5 billion light-year radius is the sphere from which light had time to reach us given the entire history of cosmic expansion. Beyond that sphere, there is more universe. We just cannot see it. The Earth, against the observable universe, is a subnuclear particle in a volume the size of the Earth. This is the final scale. And it is not even the edge of the universe, only the edge of what we can see. Chapter 10. The compounding smallness. Every scale at once. We have been building the scale comparison one level at a time, but the power of the comparison comes not from any single step, not from the Earth to the Moon, nor from the solar system to the Milky Way, nor from the Milky Way to the observable universe, but from all of them together, compounded simultaneously. The Earth is small relative to the Moon, which is small relative to the Sun, which is small relative to the solar system, which is small relative to the galaxy, which is small relative to the local group, which is small relative to Laniakea, which is small relative to the observable universe. Every step is small relative to the observable universe to the observable universe. Every step is a multiplication of smallness, and the cumulative product of all those multiplications is the number 6.9 times 10 to the 22nd power. It helps to lay out the full comparison as a chain. At each step, the ratio is the factor by which the larger structure exceeds the previous one in linear size. Earth to Moon distance. The Moon is about 30 Earth diameters away. Not dramatic yet. Earth to Sun. The Sun is 109 times wider than the Earth. The first uncomfortable step. Earth orbit to solar system, heliopause. The solar system is about 200 times the radius of Earth's orbit, meaning the heliopause is roughly 400 times the orbital diameter, or about 85,000 times Earth's diameter. We are already at 5 orders of magnitude. Solar system to nearest star. Alpha Centauri is about 268,000 astronomical units from the Sun. The solar system to the nearest star ratio in linear distance is roughly 2,700 times the heliopause distance. We are now at 8 or 9 orders of magnitude above Earth's size. Nearest star to Milky Way. The Milky Way is 100,000 light years across. The Earth-Sun distance is 8 light minutes. The ratio is about 660 million, another factor of hundreds of millions. We are now at roughly 17 orders of magnitude above Earth's diameter. Milky Way to local group. The local group is roughly 100 times the Milky Way's diameter. Another factor of 100. Local group to Laniakea. Laniakea is roughly 50 times the local group's diameter. Laniakea to observable universe. The observable universe is roughly 180 times the diameter of Laniakea. And the product of all of these ratios, from Earth to the observable universe, is the 6.9 times 10 to the 22nd power. We calculated 22 orders of magnitude, 10 to the 22nd power, a 1 followed by 22 zeros. And critically, this is a linear ratio, not a volume ratio. In 3 dimensions, the volume ratio is the cube of the linear ratio, 10 to the power of 66. The observable universe is 10 to the power of 66 times larger in volume than the Earth. A 1 followed by 66 zeros. This number, 10 to the power of 66, is the volumetric scale ratio of the observable universe to the Earth. To put it in context, the total number of atoms in the observable universe is estimated to be approximately 10 to the power of 80. The total number of atoms in the Earth is approximately 10 to the power of 50. The ratio between those two numbers is 10 to the power of 30. So the volume ratio of the observable universe to the Earth, 10 to the power of 66, is actually much larger than the ratio of the number of atoms in the universe to the number of atoms in the Earth. The Earth is smaller relative to the universe than a single atom is relative to the Earth, and then smaller again, and then smaller again. At some point, the numbers stop producing any sensory or emotional response. They become purely abstract, purely mathematical, detached from any experience that the brain can generate. This is not a failure of intelligence. It is a fundamental cognitive limitation. Human beings evolved to navigate environments at scales ranging from perhaps a millimeter, the size of a small insect, to to perhaps 1,000 kilometers, the scale of a long migration. The 22 orders of magnitude between the Earth and the observable universe span a range that is 19 orders of magnitude beyond the top of that evolutionarily relevant scale. There is no reason to expect the human brain to produce an intuitive sense of this, any more than a calculator designed for addition has a built-in trigonometry function. We are using the wrong instrument. The right instrument is mathematics, and the mathematics says 10 to the power of 22. The emotional resonance of that number is the sound of the instrument failing. Not a problem with the number, but an honest report on the limits of the instrument. This cognitive limitation has a name in psychology. It is sometimes called scope insensitivity or scope neglect. Experiments in decision research have repeatedly found that human beings respond to differences in scale, even enormous differences, with surprisingly similar emotional intensity. A study that asks people how much they would pay to save 2,000 birds, 20,000 birds, or 200,000 birds from drowning typically finds that people offer roughly the same amount, regardless of the number. The emotional response to birds are drowning does not scale linearly with the number of birds. It saturates quickly. The brain generates the same feeling of concern for 2,000 as for 200,000, not because it does not intellectually know the difference, but because the emotional system that drives intuitive valuation and concern is not calibrated for large numbers. It was calibrated for small groups, immediate threats, and local consequences. The environment of evolutionary adaptation. The same saturation applies to spatial scale. You feel the Earth to Moon distance as large. You feel the Earth to Sun distance as large. You feel the Milky Way as large. But the feelings are not proportional to the actual differences in scale, because the emotional system tops out at a few orders of magnitude and then plateaus. The difference between 10 to the 7th power and 10 to the 22nd power, between the Earth to Moon distance and the observable universe, does not register emotionally with a ratio of 10 quadrillion to 1. It registers as very large and even more very large. Both feel like big numbers. The brain has one adjective, and it applies it across 15 orders of magnitude without differentiating them. This is worth knowing because it means that the genuine scale of the comparison, the actual, mathematical, astronomical scale, is almost certainly not landing with the weight it deserves. The numbers in this video are not dramatic exaggerations. They are underestimates of the emotional impact that the actual scale should produce if the brain were an accurate instrument for experiencing it. Chapter 11, The Pale Blue Dot Revisited. What the smallness actually means. We began with the pale blue dot, a pixel of light in a streak of camera artifact 6 billion kilometers from home. Carl Sagan's commentary on that photograph, read at Cornell University in 1994, 2 years before his death, is one of the most celebrated passages in the literature of popular science, and it is worth engaging with directly, because it makes a specific claim about the meaning of the Earth's smallness that deserves careful examination. The photograph itself nearly wasn't taken. Sagan had proposed to NASA as early as 1981 that Voyager 1, after completing its planetary encounters, should be instructed to turn its camera back and photograph the planets of the solar system from the outside looking in, a family portrait of the solar system as seen from interstellar space. The proposal was not immediately approved. NASA engineers were concerned about pointing the camera near the sun, which could damage the camera sensors. The proposal sat for years. It was not until 1990, after Voyager 1 had crossed the orbit of Pluto and was safely distant enough, that the instructions were finally uploaded. On February 14, 1990, Voyager 1 turned its camera and took 60 frames of the solar system, including the image that would become one of the most iconic photographs in history. When the image was processed and the pale blue dot was identified, it covered less than a single pixel of the 640,000 pixel camera. Even Sagan was struck. He described the experience of seeing it for the first time as affecting. Here was the Earth, from 6 billion kilometers. Not the blue marble of the Apollo photographs, not the clouded sphere with its continents and oceans, visible, but a point of light almost indistinguishable from noise. Everything. 1 pixel. Sagan wrote, "Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves," he went on. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. The argument Sagan was making was not merely about physical scale. It was about humility. The smallness of the Earth, he was saying, is an argument against the kinds of human parochialism, tribalism, and self-importance that have driven most of the suffering in recorded history. The borders on maps, the wars fought over lines in the dirt, the hierarchies of importance constructed within and between nations and religions and races. All of it, Sagan was saying, is revealed as absurd by the photogram. You cannot look at the pale blue dot and maintain that any particular patch of it is uniquely worthy of violence. This is a compelling argument. It is also, strictly speaking, a non sequitur. The physical smallness of a thing does not determine its ethical significance. A human brain is much smaller than a mountain, but the mountain has no experiences, no relationships, no capacity for suffering or joy. Physical scale and moral weight are independent axes. The Earth being a sub-nuclear particle against the observable universe does not by itself tell us anything about what matters or what we should do. It does not make suffering less real or kindness less important. It does not dissolve the significance of any particular human life. But there is a version of Sagan's point that does not depend on conflating physical scale with moral significance, and that version is worth preserving. The physical smallness of the Earth is not an argument against caring about what happens here. It is an argument for a specific kind of attention, the attention of someone who knows they are in a rare and improbable place. The Earth is small, and the Earth is also, as far as we can tell, the only place in the observable universe where anyone is asking how small it is. Those two facts, taken together, are remarkable in a way that Sagan's formulation gestures toward, but does not quite reach. The physical smallness of the Earth is not humbling in the sense of being diminishing. It is humbling in the sense of being clarifying. It clarifies what is actually extraordinary here. Not the physical mass of the planet. That is unremarkable. Not the composition, carbon, oxygen, hydrogen, iron, the same elements found everywhere in the universe. not the location, an outer arm of a middling galaxy, in the outskirts of a small galaxy cluster, in an ordinary region of a supercluster, in an unexceptional part of the cosmic web. What is extraordinary is the arrangement, the specific configuration of matter. A planet with liquid water, a moderately sized moon producing tides, a magnetic field deflecting the solar wind, a tilted axis producing seasons, a specific atmospheric chemistry, a geological history that includes both the stability needed for complex chemistry and the instability needed for evolutionary pressure, and 4 billion years of unbroken biological evolution, is something that, to our knowledge, has occurred exactly once in the observable universe. It may have occurred elsewhere. The estimates for potentially habitable planets in the Milky Way alone run into the billions, but we have no confirmed evidence of it elsewhere. We are, at this moment, the single confirmed data point of complex, self-aware life in a universe containing 2 × 10 to the 23rd power stars. A sample size of 1. The Earth, despite its physical smallness, is the entire empirical basis for the claim that the universe produces complexity and consciousness. Every piece of evidence we have for the existence of observers in the cosmos comes from this sub-nuclear speck. This is the correct way to feel the weight of the comparison, not as a reason for despair about human smallness, but as a reason for something closer to vertigo at the improbability of the exception. The universe is mostly nothing. In the nothing, there are galaxies. In the galaxies, there are stars. Around some stars, there are planets. On at least one planet, there is a thin film of chemistry complex enough to ask where it came from. That is the Earth. That is us. And the distance from mostly nothing to thin film of self-aware chemistry is 22 orders of magnitude of scale, 13.8 billion years of time, and a sequence of physical and chemical contingencies that we do not yet fully understand. The pale blue dot is not frightening because it is small. It is astonishing because of what it contains, and because what it contains is apparently so rare that we cannot find it anywhere else in the vastness around it. Chapter 12. Other Earths, the scale of what might be out there. The Earth is small, the universe is vast, and the universe has been producing planets, hundreds of billions of them in the Milky Way alone, for most of its 13.8 billion year history. The question of whether other Earths exist is not primarily a question about physics or chemistry. It is a question about probability in a large number of trials. And the number of trials is so large that even modest probabilities produce enormous absolute numbers of outcomes. The study of planets outside the solar system, exoplanets, has transformed in the last 30 years from a theoretical possibility to a richly empirical science. The first confirmed detection of an exoplanet orbiting a sun-like star was made in 1995, when Michel Mayer and Didier Queloz detected 51 Pegasi b, a hot Jupiter, a gas giant orbiting extraordinarily close to its parent star. Using the radial velocity method, measuring the Doppler shift of the star's spectral lines caused by the planet's gravitational tug. Mayer and Queloz received the Nobel Prize in Physics in 2019 for this discovery. Since then, the number of confirmed exoplanets has grown to over 5,500 as of 2024, with thousands more candidates awaiting confirmation. The Kepler Space Telescope, operational from 2009 to 2018, revolutionized the field by discovering planets using the transit method, measuring the tiny dimming of a star's light as a planet passes in front of it. Kepler surveyed approximately 150,000 stars in a fixed patch of sky and found over 2,600 confirmed planets and more than 2,000 candidates. From Kepler's statistics, astronomers derived one of the most important numbers in modern astrophysics: the occurrence rate of Earth-sized planets in the habitable zones of their stars, the range of orbital distances where liquid water could exist on a planet's surface. The number Kepler pointed toward, later refined by analyses of the full Kepler dataset and by the follow-on TESS mission, is that approximately 20 to 50% of Sun-like stars, FGK stars, host an Earth-sized planet in their habitable zone. For the more numerous red dwarf stars, M-dwarfs, the occurrence rate may be even higher. Combining this with the number of stars in the Milky Way, the estimates for potentially Earth-like planets in our galaxy alone range from roughly 10 billion to perhaps 100 billion or more. 10 to 100 billion Earth-like planets in the Milky Way, in a universe with 2 trillion galaxies. The TESS mission, Transiting Exoplanet Survey Satellite, launched in 2018, is surveying the entire sky rather than a single patch, focusing on the nearest and brightest stars, the ones whose planets will be accessible to follow-up observations by larger telescopes. The James Webb Space Telescope, operational since 2022, is beginning to characterize the atmospheres of exoplanets, measuring the transmission spectra of planetary atmospheres as the planet transits its star, looking for specific molecular signatures. JWST has already detected carbon dioxide and water vapor in the atmospheres of exoplanets and is probing the atmospheres of Earth-sized planets in the habitable zones of nearby red dwarf stars. In 2023, JWST observations of the TRAPPIST-1 system, a red dwarf star with 7 rocky planets, 3 of which are in the habitable zone at a distance of about 40 light-years, began to constrain the atmospheric properties of those planets. TRAPPIST-1 is perhaps the most studied planetary system after our own, and the question of whether any of its habitable zone planets have liquid water on their surfaces is one of the most intensely monitored open questions in exoplanet science. The TRAPPIST-1 planets represent a specific and instructive case. TRAPPIST-1 is an ultra-cool red dwarf, smaller, cooler, and dimmer than the Sun, and its 7 planets orbit much closer to it than Earth orbits the Sun, receiving similar amounts of stellar radiation to the habitable zone Earth equivalents despite being much closer in absolute distance. The innermost planets are likely too hot for liquid water, the outermost too cold. But the middle planets, TRAPPIST-1, E, F, and G, are in the range where liquid water is theoretically possible if they have the right atmospheric composition and pressure. Whether any of them have such atmospheres, whether those atmospheres have survived the intense UV and X-ray radiation from the young red dwarf, and whether the planets are geologically active enough to replenish atmospheric gases. These questions are being actively investigated by JWST and will occupy planetary astronomers for the next decade. The atmospheres of these planets are where the most profound potential discoveries await. A planet with an atmosphere in chemical disequilibrium, with the coexistence of chemically reactive gases like oxygen and methane that would quickly react and disappear without continuous biological production, would be suggestive of life. A planet with large concentrations of oxygen produced and maintained over geological timescales would be even more suggestive. JWST cannot yet make these detections for Earth-like planets. The signal is too faint and the observations too noisy. But the next generation of extremely large ground-based telescopes, including the 39-meter Extremely Large Telescope, ELT, currently under construction in Chile, and proposed future space missions like NASA's Habitable Worlds Observatory, are being specifically designed to search for these biosignatures in the atmospheres of nearby Earth-like planets. What does this mean for the scale of the Earth? It means that Earth may not be as unique a configuration as the rarity of confirmed examples currently suggests. The physical parameters that define the Earth, a rocky planet, roughly 1 Earth mass, roughly 1 astronomical unit from a G-type star with liquid water, appear to occur with a frequency of perhaps 1 in 5 or 1 in 10 for Sun-like stars. The Earth's specific history, the specific sequence of contingent events that produced this particular biosphere, this particular evolutionary tree, these particular molecules and organisms, may be unique. But the physical platform, a warm, wet, rocky world in the habitable zone of a stable star, that may be one of the most common types of planetary object in the galaxy. The galaxy may be full of Earths, and the universe may contain, in its 2 trillion galaxies, something on the order of 10 to the 22nd power to 10 to the 23rd power Earth-like planets. That number, 10 to 100 sextillion Earth-like planets, is comparable to the 6.9 times 10 to the 22nd power ratio of the observable universe to the Earth in linear size. There are, potentially, as many Earth-like planets in the observable universe as the observable universe is wider than the Earth. The scale of cosmic emptiness and the scale of cosmic potential fertility are, by this estimate, roughly matched. Whether any of these other Earths have produced life, and whether any of that life has produced the specific kind of complex, technological, self-aware existence that we represent, is unknown. The Fermi paradox remains unresolved. The silence of the sky is still unexplained, but the physical Earth, in the context of what the universe can produce, is not uniquely special as a type of world. It is, potentially, one of a vast multitude of similar worlds scattered through the galaxies at a density determined by the statistics of star formation and planet formation. What is special about Earth, what may be unique, is not its physical character, but its particular history. The Earth is small. There may be many small rocks like it, but this one woke up. Chapter 13. The atom and the universe scale in both directions. We have been measuring the Earth against the largest scales, zooming out from the Earth to the moon, to the sun, to the galaxy, to the observable universe. But scale works in both directions. The same cognitive vertigo that comes from comparing the Earth to the observable universe can be induced by comparing the Earth to the smallest structures within it. And the inward journey illuminates the outward one. The Earth has a diameter of 12,742 kilometers. A human being is roughly 1.7 meters tall. The ratio of the Earth's diameter to a human body is about 7.5 million. The Earth is 7.5 million times taller than a person. A person stands to the Earth roughly as a grain of sand stands to a building. A human cell is approximately 10 micrometers in diameter, 1/100th of a millimeter. The ratio of a human body to a human cell is about 170,000 to 1. A bacterium is about 1 micrometer across, 10 times smaller than a human cell. The ratio of a human body to a bacterium is about 1.7 million. These ratios are already beyond comfortable intuition, but they are at least in the range of things that can be seen with a microscope. An atom. A hydrogen atom. The smallest is approximately 0.1 nanometers in diameter, or 10 to the power of -10 meters. The ratio of a human body to a hydrogen atom is about 1.7 times 10 to the power of 10, 17 billion. The ratio of the Earth to a hydrogen atom is about 1.3 times 10 to the 17th power, 130 quadrillion. These ratios are large, but still smaller than the ratio of the observable universe to the Earth, 10 to the 22nd power. The outward journey from Earth to the observable universe spans more orders of magnitude than the inward journey from Earth to the atom. The universe is more vast above the Earth than the Earth is vast above the atom. But we do not stop at atoms. Inside atoms there are nuclei, and inside nuclei there are protons and neutrons, and inside protons and neutrons there are quarks. The nucleus of a hydrogen atom, a single proton, has a diameter of approximately 1.7 times 10 to the power of -15 meters, or 1.7 femtometers. The ratio of the hydrogen atom to its nucleus is about 60,000. An atom is 60,000 times wider than its own nucleus. If an atom were the size of a football stadium, the nucleus would be a pea at the center. You have certainly heard this comparison before. What is less often noted is that the football stadium to pea ratio, 60,000, is the internal emptiness of a single atom. An atom is almost entirely empty space. The atom is mostly void. And the Earth, which is made of atoms, inherits this emptiness. If you somehow squeezed all the empty space out of the atoms in the Earth, compressed all the nuclei and electrons together with no gaps between them, the resulting object would be roughly the size of a large football stadium. The entire Earth, all 6 times 10 to the 24th power kilograms of it, in a structure about 300 meters across. This is what a neutron star is, a stellar remnant in which the collapse of the core during a supernova has crushed the atomic nuclei together, eliminating the empty space between them and producing an object roughly 20 kilometers in diameter that contains 1.4 to 2 solar masses. The crushed nuclear matter of a star that was once perhaps 10 times the mass of the Sun. The Earth is small compared to the observable universe. The atoms making up the Earth are small compared to the Earth. The nuclei of those atoms are small compared to the atoms. The quarks inside those nuclei are small compared to the nuclei. The inward journey and the outward journey are both journeys through vast ranges of scale, and the Earth sits somewhere in the middle, not at the top and not at the bottom, but at the particular scale at which the physics of chemistry and biology happen to operate. The scale at which liquid water is possible, at which molecules can form the complex structures necessary for life, at which electromagnetic radiation from a star can warm a surface to biologically relevant temperatures without destroying the chemistry it needs to support. There is a reason the Earth is the size it is. It is not an accident that habitable planets are in the range of a few 1,000 to 10,000 kilometers across, rather than being the size of an atom or the size of a galaxy. Planets smaller than a few hundred kilometers cannot maintain the spherical shape, geological activity, or atmospheric retention necessary for complex surface chemistry. Planets larger than roughly 10 Earth masses tend to accrete thick hydrogen-helium envelopes that produce gas giants rather than rocky planets with solid, potentially habitable surfaces. The habitable planet size range is determined by the physics of planetary formation and atmospheric retention, and the Earth sits squarely within it. The Earth is the size of a potentially habitable rocky planet because that is what it is. Its size is not random. It is constrained by the physics that makes it biologically relevant. But biologically relevant scale is still in absolute terms subnuclear against the observable universe. The fact that the Earth's size is physically meaningful for life does not make it physically meaningful in the context of the cosmos. The cosmos does not notice biologically relevant scales. The cosmos does not notice anything. The scales at which biology operates, from a few nanometers, the scale of a DNA helix, to a few tens of thousands of kilometers, the scale of a large planet, are a tiny, specific window within the full range of scales the universe operates across, from the Planck length at 10 to the power of minus 35 meters to the observable universe at 10 to the power of 26 meters. That window is about 61 orders of magnitude wide out of a total range of about 61 orders of magnitude. Biology occupies, very roughly, the middle third of the full-scale range of the universe. We are not at the smallest scale, and not at the largest. We are somewhere in the middle, looking out in both directions at ranges of scale that equally defeat our intuition. What is striking about this bidirectional smallness, the smallness of atoms relative to the Earth, and the smallness of the Earth relative to the universe, is that both are expressions of the same underlying fact. The universe spans an enormous range of scales, and complex chemistry happens to be possible only within a narrow band of that range. Too small, and quantum effects dominate all chemistry in ways incompatible with stable molecules. Too large, and gravity dominates in ways incompatible with the delicate electromagnetic structures of biology. Life, if the Earth is a representative example, exists at precisely the scale where the electromagnetic force and gravity are both present and roughly balanced at the relevant sizes of structures. Atoms are small enough to be quantum mechanical, but large enough to form stable molecular bonds. Planets are large enough to retain atmospheres and generate internal heat, but small enough that their surface gravity does not crush chemistry. Stars are large enough to sustain nuclear fusion, but small enough that their radiation field does not sterilize all nearby surfaces. The entire stack of life, from DNA to cells to organisms to planets to stars, sits in a specific window of the universal scale range where each level of structure is possible. Outside that window, in either direction, the physics changes in ways that do not support the complexity we represent. The Earth is small in the context of the universe, but it is exactly the right size for what it is trying to do. Chapter 14. the coordinates of the Earth, our full cosmic address, given everything we have covered, the moon, the sun, the solar system, the galaxy, the local group, Laniakea, the observable universe, it is worth assembling the full cosmic address of the Earth, not as a parlor trick, but as a way of making vivid, in one place, how many nested layers of structure exist between here and the universe. The Earth is the third planet from the Sun. It orbits a G-type main sequence star of mass 1 solar mass, at a distance of 1 astronomical unit, 149.6 million kilometers. The Sun is one of approximately 200 to 400 billion stars in the Milky Way galaxy, a barred spiral galaxy of mass approximately 10 to the 12th power solar masses, diameter approximately 100,000 light-years. Within the Milky Way, the Sun is located approximately 26,000 light-years from the galactic center in the Orion Arm, a minor spiral spur, at a galactic longitude of about 26 degrees. The Sun's position in the galactic disk is approximately 20 to 30 light-years above the galactic midplane. The Milky Way is one of roughly 80 galaxies in the local group, a gravitationally bound cluster spanning approximately 10 million light-years, with the Milky Way and Andromeda as its two dominant members. The local group is part of the Virgo supercluster, a large-scale structure approximately 110 million light-years across, centered on the Virgo cluster, and falls within the larger supercluster structure of Laniakea. Approximately 520 million light-years in diameter, which is itself one node in the cosmic web's network of filaments and voids. Beyond Laniakea, the next recognizable large-scale features include the Hercules Corona Borealis Great Wall, a filamentary structure approximately 10 billion light-years in extent, one of the largest known structures in the observable universe, and the cosmic web itself, whose full extent fills the observable sphere of 46.5 billion light-years radius in every direction. The full address: Earth, Solar System, Orion Arm, Milky Way, Local Group, Virgo Supercluster, Laniakea, Observable Universe. 8 levels of nesting, each containing the previous like a Russian doll, each larger by factors ranging from tens to millions. Each of these 8 levels has its own dynamics, its own history, its own character, and the Earth participates in all of them simultaneously. Right now, as you read this, the Earth is orbiting the Sun at 30 kilometers per second. The Sun is orbiting the galactic center at 220 kilometers per second. The Milky Way and Andromeda are falling toward each other at 110 kilometers per second. The local group is falling toward the Virgo cluster at roughly 300 kilometers per second. The entire Laniakea supercluster is streaming toward the Great Attractor at roughly 600 kilometers per second relative to the CMB rest frame. And all of this is happening simultaneously, all the time, invisibly, at every moment of every day. The Earth is not stationary. It has never been stationary. It is a passenger on a nested cascade of motions. From the daily rotation of the planet itself, to the orbital dance around the Sun, to the galactic orbit, to the supercluster infall. Each motion caused by the gravitational influence of the structure one level up. Every point on the Earth's surface is, at any given moment, moving through space at the vector sum of all these velocities simultaneously. The experience of standing still is an illusion produced by the fact that everything around you is moving in roughly the same direction at roughly the same speed. If you were able to somehow stop all these motions and hover at rest relative to the CMB, the closest thing to a true rest frame in the observable universe, and watch the Earth from outside, you would see it hurtling through space at a combined velocity of over 600 kilometers per second, carrying its passengers along for the ride toward a gravitational attractor, hundreds of millions of light years away, in a universe expanding in all directions at once. The Earth is not sitting here waiting. It is going somewhere. It just isn't going anywhere that matters on human timescales. If you were giving your cosmic address to an alien civilization on the other side of the observable universe, you would need to specify all 8 levels before they could even begin to narrow down your location to within 1 billion light years. And even then, even with the full address, with all 8 levels specified, they would need to know the precise galaxy, the precise stellar system, the precise planet, the precise location on that planet before they could find you in any operational sense. The universe is large enough that a complete and accurate cosmic address is still insufficient to locate a specific planet without additional precision. The Earth is not merely small, it is small and specific and improbable. Small in the sense of its physical size relative to the cosmos. Specific in the sense of its position within an 8-level nested hierarchy of structures, each with its own dynamics, history, and character. And improbable in the sense that the particular physical history that produced this particular planet, at this particular location in this particular galaxy, at this particular moment in cosmic time, is a history that, as far as we can determine, has not been exactly replicated anywhere else in the observable universe. Conclusion. So this is how small the Earth is compared to the universe. The Earth is 12,742 kilometers in diameter. The observable universe is approximately 93 billion light years in diameter, roughly 880 sextillion kilometers. The ratio between these two numbers is about 69 sextillion to 6.9 times 10 to the 22nd power. The observable universe is 69 sextillion times wider than the Earth. In 3 dimensions, in volume, the ratio is 10 to the power of 66. There is no analogy that captures this. The analogy breaks. The number is what it is. We built this comparison step by step. Earth to Moon, 30 Earth diameters. Moon to Sun, 109 Earth diameters across. Sun to solar system edge, 85,000 Earth diameters. Solar system to nearest star, hundreds of millions of Earth diameters. Nearest star to Milky Way, 17 orders of magnitude above Earth's size. Milky Way to local group to Laniakea, Laniakea to the observable universe, 22 orders of magnitude in total. At every step, the Earth became smaller. At the scale of the Milky Way, it was 1/4 the width of a human hair in a continental scale model. At the scale of the nearest star, it was smaller than an atom in a 1-meter model. At the scale of the observable universe, it is subnuclear. And at every step, the brain applied the same rough heuristic, very large, and moved on without fully processing the actual ratio. This is not a flaw in anyone watching this video. It is a feature of the cognitive instrument we all use. The brain was not built for this. The emotional and intuitive systems that process scale were calibrated for the Pleistocene savanna, not for a 93 billion light-year observable sphere. The fact that we can compute the ratio and write it down is already remarkable. That we can feel the ratio, even faintly, is the product of the specifically human capacity for abstract reasoning applied to physical reality. Mathematics is the extension of human cognition into domains the unaided brain cannot reach. The ratio 6.9 times 10 to the 22nd power is something mathematics can hold, even when the brain cannot. There is something else to sit with here which rarely gets said directly. The process of building this comparison, moving outward from the earth, step by step, accumulating scale, is itself a demonstration of what makes the earth remarkable. We built the comparison, not the universe, not the Milky Way, not the solar system. A particular arrangement of atoms on the surface of a subnuclear speck built the comparison, using instruments of metal and glass and silicon that it constructed from the materials of that same speck. The Hubble Space Telescope, which gave us deep field images of 10,000 galaxies in a patch of sky the size of a grain of sand held at arm's length, was built in a factory in Danbury, Connecticut, using materials mined from the earth, designed by people who lived their entire lives on the Earth's surface, launched from a rocket assembled in Florida. Every number in this video comes from instruments and methods that human beings built on this small rock, measuring a universe 10 to the power of 22 times wider than it. And yet, somewhere inside those 22 orders of magnitude of smallness, somewhere on the surface of this atom-sized point in a universe-scale model, something happened that has not, as far as we can confirm, happened anywhere else in the observable universe. Chemistry became biology. Biology became complexity. Complexity became nervous systems. Nervous systems became consciousness. Consciousness became curiosity. And curiosity looked up at the sky and asked, "How large is this? How small are we?" The universe did not ask this question. The Milky Way did not ask it. The solar system did not ask it. The Earth, strictly speaking, did not ask it. A specific configuration of atoms on the surface of the Earth. A configuration that required 4.5 billion years of planetary history and 3.8 billion years of biological evolution to produce, asked it. And the answer it found was very large, incomprehensibly, subnuclearly, mathematics breakingly large. Carl Sagan called the Earth a pale blue dot, and he was right. But a pale blue dot that contains within it every act of human courage and cowardice, every civilization, every discovery, every love, every loss. That dot is doing something that the rest of the pale dots in the universe, as far as we know, are not. It is thinking about its own smallness. It is measuring itself against the cosmos. It is against all physical odds aware. The Earth is small. It is unimaginably, vertiginously, irreducibly small. And it is also, in the only sense that currently matters to anyone who can appreciate the comparison, the most interesting object in the observable universe. Both of those things are true. Sit with them.